My name is Doug Stevenson. I'm a developer advocate with the Firebase team.
And I'm Sarah Allen. I'm an engineering manager at Google. And I'm super excited. I actually got a chance to code on some of the technology that we'll be talking about today. So Planetary Scale apps with Firebase Planetary Scale is what we're talking about today. And that means huge data sets, billions of people across the planet using your app. This talk is really for two kinds of people. Some of you maybe already have a Planet Scale app. And you're thinking, I have so much going on. How could I possibly use the new technology? It's very hard, even though everybody wants to do that. With some of the technologies we're talking about today, there's an opportunity to reduce the ops burden and add features more quickly, increasing your velocity. The other kind of person, and I think this speaks to every one of us, we have in the back of our minds or our forefront of our minds a world-changing idea. Something that is a small app now, or a small idea wanting to be an app that aspires to be a planet scale app. And I'm really excited to share some of the technologies that can let you build small and grow big. So specifically, what do I mean by planetary scale? So this is the technology that will help you reach every person on the planet, potentially connecting to 4 billion people that are now connected to the internet with lots of data. So anytime you have a lot of users, you have a lot of data. Sometimes you have fewer users and a lot of data. And it's too big to fit on one hard drive. It's complicated sometimes to design queries to get the data you want that is responsive and quick. And you want your data to be close to the edge. So wherever on the planet your users are, the data gets to them quickly. So I've described some of the challenges, but the good news is with a mobile or web app, no matter what technology you're using, you only need to fetch the amount of data as fits on a screen, or maybe a few screens. And so this is a hard problem to get right, but it's a totally solvable problem because it's constrained by the amount of data a human can see on a screen.
So in this talk, we'll show 2 examples of planetary scale apps. One is a real-world use case, so an app that maybe you use, you maybe already used it today. And there's an app that we built. We're going to demo it for you today. When did we finish this demo?
I think we were still working on it as we were walking here.
Moments ago, yes. So hopefully the demo gods are shining on us right now. And we'll open source that later so you can explore it on your own at your own time. So the tool that we used, well, that both the other app that we'll show you later and our app they both have in common is Cloud Firestore. So Cloud Firestore is a massively scalable NoSQL database. It's cloud hosted, so all your data lives in the cloud if you're using Firestore. And how is it scalable? Well, what does it mean by massively scalable? Well, the idea is that when you query it, you want to query the data that you get out of it. The performance is based on the size of your result set. So what you query out of it determines the performance. So what does that mean? So say you have 50 documents in a day, or say you have 1,000 documents in a database and you query for 50. That's not a very hard problem to solve, but the performance is based on the 50 that you query for. Now, what if you have 100,000 items in your database? Well, as long as you're still querying for 50, the performance is exactly the same. And what about 100 million? Well, still, with Firestore, it scales such that if you're querying for 50 documents within that 100 million, you're still getting the same performance. It scales massively, not with the size of your entire data, but with the size of your result set for your query. And it's effortless. There's no sharding. There's no maintenance. You just write the queries. Populate the database, of course, then write queries on top of that.
So I'm really excited to share with you our first use case, which is Evernote. With their hundreds of thousands of users, they currently support a lot of infrastructure. They were looking for a way to increase their velocity, lower their ops burden, and deliver new features to their customers all at the same time. When we met with them, they mentioned some of the primary reasons for choosing Firestore. These aren't the same ones that everybody picks, and I thought this was really insightful. They are really excited about the offline support. So the client SDKs allow for writing when you're disconnected and then automatically syncing to the server when you get back online. Also, there's notification of change across multiple devices. And the consistent APIs across the client SDKs really speed development, and they're super excited about that. So in addition to sharing notes, Evernote users often use multiple devices. They might use their desktop app and their mobile app at the same time, or maybe they use their desktop app at work, and then at home they use their tablet. And people more and more expect this kind of seamless experience, but particularly with this app where everybody's keeping their really important personal data and observations on the world. So before we dive into that, I wanted to take a moment and tell you about Firebase Rules. And this is really a key part of what makes Firestore and all of the Firebase accessible data storage options really work well. Normally, you need a server in between your client and your server-side data, because you can't just have those queries open to the world. You have to do some authorization. You have to do some validation. There's a whole bunch of things that you just normally have to do. They're not fancy. They're just stuff that is important. And so with Firebase Rules is a simple declarative syntax that you just upload to the server, and that says which of your data paths are accessible. So only authorized users can read and write certain documents. You can also have public data. You can have data that's not accessible at all, except on the server side. You can also do validation where you limit the length of a string, or make sure integers are within a valid range. So Doug, why don't you tell us a little bit more about Firestore?
I will do that. So Firestore data modeling is kind of particular. So it's derived from what we learned from users of Firebase real-time database. So for those of you who have already used that, it's also a cloud-hosted NoSQL database. And what we did is we observed what developers were doing with it. We found some patterns, some best practices, and what we did is we tried to code that into the structuring of Firestore. So what you'll see is that it mirrors the most common use cases. So what you have is at the very top level of your Firebase, you have collections. And these collections are containers for documents. You have to organize your documents into collections. A document is the lowest level unit of data. So there is nothing really smaller than a document. But a document can have fields in it, and those fields can have type values. So when you read a document, you're getting all those fields, all those data types, all in one query. Now, within a collection, documents can be ordered, and they can be filtered based on the content. So if you have fields in there that you want to use to narrow down your search or order by, say, date or some count or something like that, you can perform queries like that, and like I said, that scales with the size of your result set.
So I'm really excited that Evernote decided that they were willing to share a bit about how their data is modeled. And they're doing some common patterns. So this can give you a sense of how Firestore data modeling works. So you have a top-level collection of all the users. When somebody logs in, then the client will write this data, whatever user data that they signed up with, and then you have your basic profile information. From then on, that's cached locally on the device. And when you reconnect, it listens for changes from the server, so that if you connected on a different device and changed your profile, it would automatically sync. So then they organize data in your notes in notebooks and spaces, and those you also listen to from the client side. And there's another top-level collection of all your notes. So this is a common pattern for how Firestore organizes these data. You have these top-level collections which can have a huge number of documents, but the individual user is only getting a small subset of them. And therefore, you can have that result set be small and your queries be fast. So the client listens to the notes that they have access to, and then when they change, it automatically is synced across devices and between users. And then Firebase Rules works on the server side to make sure that people can only access what they're supposed to have access to, keeping user data safe.
Now, you might be wondering, what did we build? Well, our use case is a little bit different than Evernote. It's actually just a web app. We're calling it Friendly Shop. And the idea here is, and this is totally fictional, of course, that companies all over the world can upload images with inspirational quotes. So you can think of it kind of like a shop, and the idea is that you can go and browse them and maybe buy them. What's common between the Evernote case and our case is that we don't need to show all the documents. We don't need to show all the items together. We only need to show what can fit on the screen. Or in this case, we're showing 50 items per query. So what we'll do is we'll dive into this a little bit. The idea is what our hope was, we wanted to put 1 million documents in there. We were targeting 1 million, but how many did we actually get to, unfortunately?
We got about 260,000.
260,000. We'll demo to you 260,000 items today. If I say million, that's just because we were planning on 1 million. But we didn't quite get there.
I'll get into a little bit of detail about some of the gotchas we ran into. Not a limitation of the scale of Google storage or anything like that.
Yeah, that was just our lack of planning, really. We put in a lot of stuff at the last minute.
It was our excitement and enthusiasm for adding features at the last minute.
Yes, and Sarah will talk more about how we actually populated the database. So what did we use to build it? Well, obviously we used Firestore, like we mentioned earlier, but we used a variety of Firebase and cloud products to build this out. And what we didn't have to do here is stand up a server, configure it, log into it. We didn't have to scale it. It all just happened automatically. So
first we want to tell you about, or second, because we've already talked about Firestore, Firebase hosting. For a web app, this is of course essential. But whenever you have a mobile app, typically you'll have at least a few screens that you want to deliver on the web. And you want to be able to easily serve up all your static assets, HTML, CSS, JavaScript, and images. And then you also want to be able to do this globally and have those accessible close to the edge. And Firebase hosting is a global content delivery network with physical edges all over the world. So no matter where users are, they get low latency, which turns into speed for the user experience.
So it's like planetary by definition, almost.
Exactly.
The other component we used is Firebase authentication. We used just a tiny sliver of it, but what Firebase authentication does is it helps you get your users logged into your mobile application. And it supports Google login, Facebook, Twitter, and more. If that's not enough to suit your own Planetary Scale needs, you can write your own plugin. So if you have your own authentication provider, your own users, your own OAuth system, you can plug that in yourself, and that's fine.
So cloud storage. Each poster has its own image, and we need a massively scalable data storage place to put them. We actually don't need something quite as massive as cloud storage, but it's good to know it's there. So the images can actually get pretty big, and there's room to have extra thumbnails and variants across the devices. And let me tell you a little bit about how big Google Cloud Storage is. It's exabytes of data. Had to look up what an exabyte is.
It's big.
It's really big. It's a number of bytes with 18 zeros after it, and roughly 1 million terabytes. And I don't know if anybody's old enough to remember when we had to worry about physical disks. And if things were too, like we get bigger and bigger disks, and that was like really exciting. And then if your stuff had to go on multiple disks, that's a lot of work. And it's so lovely not to have to worry about that and not to have to plan for that to be in the future. And so with our poster app, even if we were storing a really high res image that was like 10 megabytes, I could store trillions of those. And that's really delightful. And I think that it'll work for our friendly shop, even if we get to planet scale with our user base.
That's right. All right, and the last component that we use to kind of wrap all these different products up is called Cloud Functions. So with Cloud Functions, what we have is a serverless backend compute container, and it's built on top of Node.js. It's a managed Node.js environment. So all you do is write Node, write JavaScript, deploy it to Cloud Functions, and it runs in response to events that happen in your system. Now, what are those events that happen? Well, for example, what we could do in our app is when a new user signs up, we can automatically turn around, write some code, and create a user record for them. Or anytime a new doc is added, so like someone uploads a new poster, what we can do is automatically kick off some process to generate thumbnails that are appropriately sized for our web app. Or if oh, I don't have a third case. But the point is, all you do is write and deploy that code. You don't manage any servers. You don't log into anything. And best of all, you don't scale it up or down. It automatically scales up to meet the demand of your system and automatically scales down to 0 if all of your demand goes away. So you only pay for what you use. You don't have all these servers, hundreds of servers fired up, paying for them all the time. You only pay for the compute resources that you actually use with Cloud Functions. And in this product, I'll actually live add one new function that will add some functionality to our app without having to deploy a new version of the web app. So I'm excited to show you that, if it works.
So this is a truly serverless experience, which significantly simplifies both your development and your operations. This sort of illustrates how these all work together to power our friendly shop app. There's no servers, no VMs to manage. You can do capacity planning on a napkin. And having this fully managed infrastructure means that we can focus more on our application features. And that is really what drives the business value for our friendly shop. One place that we do need to do some careful thinking, as we mentioned before, is how our data is modeled. It's not auto magic. You have to think about your use case and how you're going to put that data together. And Firestore is structured to help you think through that and organize your data for scale. So I want to dive into the Firestore experience. This is an image of from the data console in the Firebase UI from our friendly shop data structures. And I'll just walk you through the interface, which also walks you through our data structure. So if the app were more real, you would probably have more collections. On the first panel on the left, you'll see items. So that will show a list of collections. Normally, it'd have items, users, whatnot. And you can also add collections direct in the interface. So being able to direct ads in the interface sometimes means that you can get started on the view of your app before you build all of the interaction into your app. The next column is a list of documents for the selected collection. And here we have 260,000 plus documents, and you could actually scroll through all of those. You can also snap to a particular ID and pick a particular document. And then when you select the document, its contents show up on the right. And here is some of the data, or all of the data for our, all the metadata for each of the posters in our shop. And you can also, our app doesn't do this, but if you want to structure your data more and deeper, you can control how much you access at a time by creating sub-collections. So you can see there that you can add a collection as well. Although our app has a fairly simple but flexible data model with just a top-level collection.
You hold on to that one. So here is how you query the database. It's just a simple few lines of JavaScript. If you go and view the source, you'll get something like this, although it's a little bit broken out. But what we do here is we're using the Firebase SDK, JavaScript SDK. We're reaching into the Firestore product for that. So Firebase has a bunch of different products bundled into it. We're just interested in Firestore right here. And we're going to reach into the items collection. And then we're going to order all those items, all 260,000 of them, by price, descending. So we'll get the most expensive one first and the least expensive ones last. And then we're going to limit by the first 50, the top 50, again, based on the ordering. Then we're going to get, that's asynchronous, and once we get those 50 results, we'll render them to the screen. This is actually how we populate the home screen for our apps. So why don't let's jump into a demo. Advance the slide, we'll jump into the demo. OK, so actually, if you want to view this demo live, see that short link up there, that bit.ly link? Go ahead and copy that into your mobile browser or your desk or your laptop or whatever, and you can actually follow along with me. So what I'll do is I'll copy this and paste it into the browser. And it loads up. And we have results. So here's 50-some, the top 50 sorted by price. So we have all the expensive ones here. Everything here is $25.99. I can actually turn around and reverse that sort if I want. And now we have the cheap ones. I'm a budget shopper, so I'm going to keep it on the cheapest ones first. So that's how we populate the home screen. Pretty straightforward. Could we go back to the slides, please?
So when we want to add an additional query, because we want to add filters, we can specify another where clause. So in this case, we want to filter by topic. So we can say where a topic equals whatever the user has picked in the interface. And then compared to the prior query is in gray, and the new part is highlighted. And this is just another option in the query builder that lets us filter the results. So let's go back to the demo and see what that looks like in the app.
OK, so what I'll do now is let's choose a topic. And these topics are all randomly generated. We used a node module called Faker. And Faker generated all this sort of like businessy sounding thing. So it's all sort of tongue-in-cheek, kind of humorous. Anyway, I'm going to filter on a topic. I'm totally into e-business, so I'm going to do e-business. And then the results come in. Notice that the queries are just as fast as all the others. Adding a where clause didn't actually impact the performance of this. But now we can see that we have all e-business posters. And I can go in there and change that again. I'm also totally into platforms. How about platforms? I'll do that.
These are inspirational posters for businesses all over the world.
That's right. And so now we have all platforms. And again, the query is exactly the same no matter how many where clauses we add. So I'm going to go back to these slides.
So now we want to add another filter. We do it in an intuitive way by adding another where clause. So these particular poster images have a range of colors. And so we can choose the top 50 posters sorted by price, starting with the most expensive. And then for a particular topic and a particular color, we can see the result set.
Yeah, so let's go to the demo again. All right, so you saw on the last page that bit of code. Those two where clauses, they're being logically anded together. So if I want to look for posters that are on the topic platforms and are in, let's do orange, because that's the closest thing to Firebase. So let's look at all the ones that are orange. And again, we get now, oh, that's actually really attractive. So again, you notice we made the query more complex by adding another where clause. But again, the query took just the same amount of time, because it's the same 50 size result set. Remember, queries scale based on the size of the result set, not on the source data set. Oh, and I should have added, or I should have mentioned earlier, we actually have a script over here that's constantly adding new. Oh, now you can see it added a new one. So this is actually simulating what users might actually be doing. Imagine there's users all over the world constantly adding new documents. That's what this script back here is doing. So the result set that you see on screen or that you're seeing in your mobile app could actually change over time. So this isn't just a static result set. This is a constantly changing result set. And this becomes significant later on. So let's switch back to the slides.
So you can keep doing this. And we could go through another one and another one and another one and keep making up variations of our posters. But we think you get the idea by now. So the only requirement is that when you're doing these composite indexes, that you create a composite queries that you get you create a composite index. And so that allows you to support all the combinations of filters and ordering that you need. So we have another demo.
Oh, no, we're talking about indexes now.
Oh.
So yeah, you can keep adding where clauses to your heart's content, But the only constraint here is that you have to add indexes for them. So what you see here is a screenshot of what it looks like in the Firebase console for the indexes we've added. So you can see we've got all the combinations of things we want to filter and order by. As long as all these indexes exist, your queries will be fast, right? And there's nothing you have to do. When you create an index, it'll just go off and do it. You can also put these in a configuration file and deploy them with your app, so you don't have to manually create any one of these. But the interesting thing here is that if you forget to create an index and you try to query on it, Firestore will say, well, I'm not going to do that query because it doesn't scale. I only do scalable things. But what it will do is give you a very interesting error message in the console. So this is an actual error message of what Firestore SDK is showing you. It says, the query requires an index. You can create it here. And it gives you a link to go create that index. You don't have to know any sort of magical incantations. You just click the link. It takes you to the Firebase console and makes that index for you. So during development, if you forget to think up all the different combinations of things you want to query on, you can just create one ad hoc. And I think that's really amazing. This is maybe the most actionable error message you will ever see in an SDK. It's literally telling you how to fix. Thank you. Thank you. We hope Firebase is easy to use.
So just wrapping up the scalable queries, as Doug has just demonstrated, indexing made easy. All of your individual fields are indexed by default. So if you're just doing a very simple query on a single property, you don't have to do anything. And then for compound queries, we have a little helper there. So I think you've seen lots of different demonstrations of how performance is based on the result set. And we have a lot of great documentation on how to structure your data. We've gone through some really common patterns today. And once you get a feel for it, then you can put together these really scalable apps. So we can also expand our app on the server side in a different way with Cloud Functions. So we talked about 2 different data storage ways to scale your app with Firestore and with cloud storage. And with Cloud Functions, you can provide server-side code. You can do a lot with Firebase with only client-side code, but server-side code can be helpful for. We have 3 things shown on the slide, which is like some data wrangling. You might, when you're creating your profile, want to get some stuff from social sharing sites or figure out who people's friends are. You might have some business logic to drive user growth with a shopping frenzy. And you often have to do a whole bunch of media wrangling, creating thumbnails and variants on images. The other kinds of things that people do with Cloud Functions is put code on the server rather than client in order to make fair decisions, in order to be really careful with that business logic and protect that so it's not kind of in the wild in an untrusted client, but secure on the server side. And then it's also a great way to do multi-party interactions, to create a bot, to coordinate many users at the same time.
So Cloud Functions has support for a bunch of different event providers within the Google infrastructure. So you've already seen Firestore and real-time database. Actually, we haven't seen it yet. We've mentioned Firestore and real-time database. What you can do with Cloud Functions is write triggers that respond to changes within your database. So in Firestore, if a document is created or changed or deleted, you can write code to respond to that. Same thing with real-time database. If something changes anywhere within the hierarchy that matches a pattern that you define, you can again write some code. So this is good for doing things like data sanitization. If you want to change a value that's invalid at the time of insertion, you can do that with a Cloud Function. With Firebase authentication triggers, you can write code that runs when someone new enters into your system. So if there's a new account created, you could go off and create a profile for them. Or if that account is deleted, you can clean up all their data so you're not paying for a lot extra storage for a user that no longer exists. For analytics triggers, you can write code that triggers in response to conversion events. So a typical conversion event is if someone buys something or if someone performs some sort of high-profile action within your app. You can write some code to respond to that and keep track of it on the back end. Cloud storage triggers let you write code that responds to when files are uploaded or changed within your cloud storage bucket. So in our app, if a poster was uploaded, we could write some code that creates the thumbnails of various sizes that are appropriate, and all in response to the upload. We don't have to know anything else. It just happens automatically. You can also use Cloud PubSub. So whenever a message is published on a PubSub topic, you can write some code to respond to that. Also, you can use Crashlytics. So if you're using Crashlytics in your iOS or Android app, those events can get triggered through Cloud Functions as well. So you can get what's called velocity alerts to know if an error happens and how severe it is among all of your users for your apps. And lastly, there's HTTP triggers. So you can write code that's basically an API endpoint, a web hook of some sort. So you can use this to create bots, as Sarah said. You can use this to create REST APIs for your app or anything, or even if you just want to do something like populate a database, which we'll talk about a little bit later. So let's switch to the demo again. OK, so remember before there was that script that was populating the database. And this has been going on about every minute or so. It adds a new poster. Now, this is simulating what users might do. Of course, it's not the real thing. But let's say I want to drive traffic to my website by creating a trigger that responds to when a new poster is uploaded. What I want to do is tweet that out to everyone and broadcast to the world, look at our new poster. So I can do that without changing any of the web app code. So what I'll do is fire up my editor here, and this is my Cloud Functions code. And I already have in my copy buffer that's not it. How about this one? I'm always prepared. All right. So this is our new function. I will walk through a sort of redacted version of it. So if we could, actually, nope, let's not switch just yet. What I'm going to do is deploy it. And while that's deploying, maybe it will pick up one of the posters that's being created by the script. So if we could switch back to the slides now. So this is kind of a stripped-down version of what basically this function is doing. We're using 3 SDKs in this. We're using the Functions SDK. We're using the Firebase Admin SDK, which gives you programmatic access to all of your Firebase features. And we're using a Twitter SDK as well. And of course, we're going to go through, initialize the Admin SDK, initialize the Twitter SDK, and then in the body of the function, we're going to define a new function. So we're going to call it tweet new items. And we're going to say, hey, Functions SDK, I want to create a Firestore trigger, and I want to pay attention to documents in the items collection with some wildcard ID. That's what the curly braces around the ID are saying. And whenever a document that matches that pattern is created, my anonymous function here is going to get invoked with a snapshot of that document and some context surrounding the request. So I'm going to reach into the context, get the ID of the document, reach into the snapshot, get the raw data. So this is like a JavaScript object representing all the data that was in the document that was created. And I'm going to build a reference to a path in, or a reference to a location in cloud storage where the poster was uploaded. So this is now, for those of you who know cloud storage, a GS URL. Or actually, no, it's a path within the bucket. We're going to generate a URL that's going, you want to go back? Just that one line. Yeah, so we're going to generate the actual URL to that poster in the web shop. So what I want to do now is advance the slide. And what we'll do is download that file from storage. So we'll download it locally in the instance that's running in Cloud Functions. And we're going to use the Twitter API to upload that image once it's downloaded. And then once we have the media ID string for the upload, we're going to turn around, build a message. So we're going to tweet a message that says, take a look at our latest poster, the name of the poster, and the URL so the user can click on it and go to the store. And then we'll attach the media ID to it so you'll get to see the poster along with the tweet. So let's go back to the demo and see what happened here. So here we are in Twitter. Let's see if we reload this page. Oh, we have some tweets. So these two things actually happened. So we had unleash granular web readiness, which is something I've always wanted to do. If we click the link, we go to the store, and we see the poster there. So it works. So we had a Firestore trigger that triggered in response to a new poster being added, and it automatically generates social media to drive traffic to our store. So I think that's pretty cool.
Very cool. So
go back to the slides, please. Thank you.
Now I'm going to just give you a whirlwind tour of how we generated the images. So this is kind of, you can imagine lots of batch jobs where this would work. I use this amazing, fun library called Fractastic to generate fractals. It turns out to be one of the great ways to create a lot of random images. And I'll just go through the code a little bit. So this is an HTTP function. So we created an add fake poster function so that we could just curl that URL. And I create a little class that generates the fractal image, one base image in grayscale, and then optionally, the script takes a parameter which can, or the lack of a parameter will tint this a whole bunch of colors. And this uses image magic that's built into that ships with Cloud Functions on the environment that you've got there. So then it creates a random image using the faker module. So we decided to use the company noun as a topic, and we get a verb and an adjective so that we put those together into an inspirational message. And then we take the images that we created earlier and we generate a unique path based on a document ID, because then we can make sure that each of these posters has a unique storage path, and we upload the poster to a bucket. Of course, this is happening multiple times for each color. And we finally get a download URL. So this can be a public URL, which is really important for the tweeting. And then we put it all together. This is kind of a subset of the data. But it just shows you, we're putting together a document, and we call set on our document reference, and that changes the data in Firestore. So we're updating both Firestore and storage in this Google Cloud function. So, and then you end up with a JSON blob like this. And so there's a couple of configuration options that we ended up using. Timeout. This can take, depending on the complexity of the fractal, 2 minutes or so. So we extended the time out. I actually increased the memory because I found out that sometimes it ended up using a lot of memory, and then that was causing things to fail occasionally. And you can also adjust your quota. So it turned out one of the challenges we ran into in the last 24 hours is we decided that we wanted to have a nice URL for our friendly shop, so we recreated the app, because that's easy. And I forgot to turn on billing. So you get a lot of free executions without even setting up billing. But if you want to make 1 million images, in fact, if you want to make 42,000, you'll get, in a very short amount of time, you'll get a quota exceeded. So you can see that I got a spike of errors there. I also had a bug where I forgot to do something with my file, and I didn't have the Twitter set up. So it's this is the health tab in the Firebase console for functions. It's really super handy for figuring out what's going on. So also, the local disk turned out to be one of the reasons that I was having things fail because of memory. Doug actually pointed out in our documentation that something I hadn't practiced that much with Google Cloud Functions, so I didn't realize this. It turns out to be handy, but it can also be a gotcha. So normally the file system is read-only. You can put whatever you want in your functions directory, and when you deploy all your functions, all of those files are available to you. You can access them locally, but if you want to write, you can write in the temp directory. But you want to use platform-independent paths so that you can still test locally and on the server, even if you have Windows locally. And it's just kind of a good idea. So normally you create a temp file like this, and then you also need to be careful to know that the local files might be there next time, or they might not. So they're good for caching something, but if you don't need them, you should delete them, because it's an in-memory file system, so it'll chew up your memory. It's super fast, and that's great, but you want to clean them up. So you want to make sure that after whatever you do, you delete the file, unless you really want to keep it there for, because you're going to reuse it next time. So in summary, Cloud Functions is server-side code without servers. We love it for that. Most people use it for core app logic, or most of the things we've talked about today. It's also like our driving user growth example. You can easily add features when your app's in motion.
Without publishing your app again. That's such a headache, right?
Without publishing your whole app. It's fabulous. And then it's also great for back-end jobs. So
Yeah, so that's how we built our app. We used a total of 5 Firebase and cloud features. Firebase hosting for content, authentication for login, Firestore for data and searching, cloud storage for all of our images, and cloud functions to do things on the back end in response to events that happen in our system. This is pretty easy. This is pretty standard application architecture for what I would consider development of a mobile app in 2018. This is, I think, the way things will go for a lot of developers. If you're building a mobile app or a web app, I would encourage you to consider an architecture like this. It's entirely serverless. You only pay for what you use. You don't stand up servers. You don't log into servers. You don't have passwords. You don't have configurations. You just write and deploy your code, focus on your app logic, and that's all you have to do to build an app these days. So that's all the content we have. We will be in the tent. If you want to ask questions, we'll be in the tent across the way over the wooden structure, and we'll see you over there soon. Thanks.